Good morning, friends. See if we can get a screen share going here. I guess we get to do that today. Isn't that nice? It is calculus time. Let's see. Let's just start off with a couple of playful things since you guys are on time. I just made a couple of cool Desmos demos. So I showed you this kind of quickly going out the door yesterday, but the rectangular equation that has x's and y's in it and sort of gives place, as you see at the top up there, for an x squared term and a y squared term and an x term and a y term. That's actually every graph there is. That's all four types of conic sections that we looked at yesterday. And then I just kind of added a note down at the bottom. I kind of dragged yesterday. I just kind of made that really quickly and just sort of dragged this around and showed different graphs. But notice right here, you can actually see them all. Like there's a hyperbola, and then it sort of flips into an ellipse. And as it gets closer, it turns into a circle. But how come I don't get a parabola? Well, I actually do get a parabola right there. Why is that a parabola? I want you to notice what I just dragged. If a is 0, why would that make a parabola? Well, notice that the ax squared term, and that fact that a is 0 took the x squared term away. So now we don't have an x squared and a y squared. We only have a y squared. So we have an x term, cx, but we don't have an x squared term. Well, you need both x squared and y squared to create circles and ellipses and so forth. And so I made a couple notes down at the bottom. They're just kind of interesting. So if you make a equal to b, so if I make b equal to, let's say 4, and I do the same exact thing with a, then I'm going to get a circle, simply because if I divided by 4, then those would both be x squared plus y squared. There would be nothing else there. So they're identical. In a sense that what that's going to do is make the what I was calling yesterday kind of the x radius and the y radius, it's going to make them identical. And so again, that's really an ellipse. It's just a special case of an ellipse. That's what's kind of cool about this. And so note I put at the bottom kind of references that if you make a equal to b, then it'll be a circle. But if they're not equal, one's bigger than the other, it doesn't really matter which one, then you're going to get an ellipse. It doesn't have to change much at all. And as I showed you yesterday, I can make it 4.1. It's still going to look like a circle. But if I make it something more like 9, it's going to be much more obviously an elliptical kind of a shape. And then I pointed out at the bottom, if a or b equals 0, then it's going to be a parabola. And then what does it take to make a hyperbola? Well, remember there was a negative sign in there yesterday. It wasn't x squared plus y squared. It was x squared minus y squared. If one of them is negative, either one of them is negative, then you're going to get a hyperbola. So notice it's interesting that you're actually only messing with a and b. Like it doesn't really matter what those other terms are, c, d, and h, those other constants. That's just because all those do is slide the graph around. So if I go mess with c, you see how it's just kind of moving the graph around. It still leaves it as an ellipse. If I mess with d, and notice what direction it messes with d. Since d is up there paired with y, it's having an effect on y. And if I mess with h is the constant that sort of determines the size of all of this. And so none of that changes the fact that it's an ellipse. That's what's kind of cool about this, I think. So anyway, that's just kind of fun to sort of play around with and understand. So if I go up here and throw a negative in front of one of these, bam, all of a sudden it's a hyperbola. And so that's kind of, in reality, that's your assignment in this section is really entirely based on rectangular coordinates or rectangular shapes. And so I wanted to spend a little bit more time with that today. So let's do this. If we look at your note sheet, I took this straight out of your book. And again, your book and My Open Math aren't necessarily speaking the same language. But in terms of kind of highlighting how to mess around with this, and the interesting ones, if you will, are the ellipses and the hyperbolas. So let's just play with this formula sheet a little bit and kind of just try to mess around a little bit, see if we can figure something out, see if we can, just mess around with graph a little bit, have a little bit of familiarity with what the graph looks like. So let's see, I'm going to make this as large as I can and take a picture of it so we can throw it inside the note sheet for today. So the funnest thing to do with this section is really to kind of play around. And I think to do that, I actually want to start and actually play around. I mentioned yesterday that I made an elliptical arch one time. And so this was kind of what happened. So my practical example for this, I had a hallway in the house that was, if I remember right, 64 inches wide. So that's how wide the hallway was. And it was like coming kind of from the entry of the house into the main house. And, normally that would be just a flat ceiling. And like when you walk under a doorway, there's kind of a flat ceiling. That's the typical kind of archway. But I thought, well, let's make an archway. That'd be kind of fun. And most people that, don't know as much math as you guys do, they'll make a circular arch like that. And that kind of looks good. That looks better. And that's because it's so easy to make, because all you need to do is drive a nail in the ground and then put a piece of string out there and then kind of stick your pencil on the end of it and then stretch the string tight. And of course, that's just going to make a circle, right? So it's super easy to make, but it's very difficult to make elliptical arch. So, and I'll tell you a couple other things about this. So elliptical arch is different in the sense that instead of starting out kind of straight off at an angle, like a sharp change, an elliptical arch, at least the top half of it, is actually going to start initially straight up, and then it'll kind of start curving from there. And so, it might look something like that. Well, again, I could have sketched that on a piece of plywood to make it and so forth. And like that sketch isn't terrible. Like if I went and cut that out, that's not terrible. But, I thought, let's make this thing really accurate. And so I was stuck with 64. In other words, I really need a 64-inch wide ellipse, but the height of it is kind of up to me. Does that make sense? I could have made that any height I want. I chose to make that height 16 inches, I remember. So I kind of just chose that for no good reason. And so in the end, I was basically thinking, okay, well, this is what I need then. Since that's 16 to the halfway point, basically I need it to be 64 inches wide. And because it was 16 to the middle, I guess that'd be 32 inches tall. Like that's the ellipse I need to make. So if I could like draw one accurately, that'd be awesome. Now, as I showed you yesterday, what does it take to produce that? Well, you've got to come in here and find these two focuses. And in my case, I drove a nail into each one of those locations. And then I've got to stretch a string that's the correct length and then trace around that, and I'll get the ellipse. And, it's kind of fun to sort of do all the math. And so I want to give you a second to kind of think about that. In light of what I said yesterday, and perhaps in light of maybe this formula, maybe these formulas over here are a little helpful. I don't know if they speak directly to this, but why don't you stare at that for a second? So question one, I need to know the string length, which I talked about yesterday. And so the string would be what we said yesterday is the sum in an ellipse, the sum of those two orange lengths, that's always the same. That's the same exact length. So I got to figure out what that length is. And then the second thing I got to figure out is kind of this focus distance. And I'll go ahead and use the language of this sheet up here, which is plus and minus C. In other words, I need to know what that distance C is right there. I got to know where to put the nails. Focus, focuses, foci. I think I'm just going to say focus. Focus sounds weird. So again, this is just kind of a practical question. I'll give you just a couple minutes.
Wouldn't you just how do I explain it? Have it to where it reflects off the center, so that way you have both sides of the string the same length, and you'll know the other leg being half the size of 32. And then with Pythagorean theorem, you can find C.
Yeah, that's exactly right. In a sense, you don't need these formulas. If the string was placed into this position, like we did yesterday, so that now you have this right triangle. Now you have a way to get C. So see if you can figure that out yourself. Or maybe just you have a good memory from yesterday. I don't know about you, but I kind of have a hard time reading note sheets like this. Like when I didn't make them myself, they just seem mysterious. It's like I have to spend a lot of time with them before I kind of get in sync. So are you able to gather from the note up there, because this is what you'd have on a test and what you might want to have sitting in front of you. Well, notice, so the concept of a major axis vertice, even there's a little bit of terminology here, but notice in our case, this is us. Our focus is on the x-axis. It's the horizontal, or major axis is horizontal. So we're sort of looking at that set of notes. So the vertice is plus or minus a. In other words, what they're saying is this length right here is a. Well, for us, since the whole thing is 64, then that means a is 32, as far as using some of those formulas. So that's our, again, that's our kind of our x radius. In other words, we said yesterday the equation was x squared over a squared. And so the x radius is 32 based on the width as being 64. And the same thing is true kind of for the minor axis, the shorter one. That means this length right here is b. And so in our case, that height was 16. And so So this is the equation we kind of looked at yesterday. We said that's what ellipses look like if they haven't been shifted left and right. Again, I'm not going to talk about this, but if I replaced x with x minus 2, then that's just going to take the graph and shift it left. But because I'm just building something, I want to put it in the easiest place possible. And notice this note at the top says this is for ellipses and hyperbolas centered at the origin, which is what I just did. In other words, don't move them around, keep it simple. So cool. So I actually know what A and B are. That's awesome, because notice there's some formulas down here that kind of tell us how to figure out the eccentricity and some of these other things based on these numbers. So I know those two. And I could just jump straight to this formula down here. Notice there's what that says is given any two of the 5 parameters, A, B, C, D, E. There's 5 parameters. E is a bit of an unfortunate choice because E stands for eccentricity here, not for Euler's constant 2.718. But basically, given any two of them, you can sort of find everything else. And in our case, look, we know A and B. We know the size of the ellipse we want, which means we can find anything else we want. So we said yesterday, and this is to Caesar's point, if this distance up here, so I could figure this out myself. I don't need these formulas. If this distance right here is 16, and we said yesterday the string length, and that's the thing that's interesting about this. We said the string length when stretched tight was actually the same as the width. In other words, the string here is 64 inches long. And therefore, when you put it in the position that Caesar suggested, that means that length there is 32. So I can see Pythagorean theorem tells me to take 32 squared and subtract 16 squared. Well, isn't that exactly what that formula says right there? I mean, we're just looking at the logic as to how you would come up with that formula instead of just using the formula that somebody tells us. So I can actually calculate C then. So that is. So the square root of 32 squared minus 16 squared is approximately 27.7. I'll just call it 27.7. So our calculation C is approximately 27.7. So in my case, that's all I needed. I went and got a string, or I made a string that was 64 inches, and I now know that focus distance. And in my case, C was like half of it. I doubled it because I needed to put the 2 nails the same distance apart. But there's no reason I can't just write 27.7. And then we won't go down this road, but I wonder, are you smart enough to turn 27.7 inches into something measurable on a tape measure that's actually measured in 16ths? Because there's no such thing as 27.7 on a tape measure, because that's 7/10. And inches are broken into 16 parts or even 32 on a tape measure. So armed with that, I had my 64-inch string, and I had my 2 nails that were 27.7 inches apart from the center. And I started drawing it, and I was like, oh man, that's really cool. It really is 16 inches tall, and it's 64 inches wide. And so then I cut it out with a jigsaw and kind of made the arch, and it was really cool. So again, that's just kind of a practical look at this. But let's go ahead and figure out the other stuff on this. That's all I needed. I didn't need to know anything about eccentricity or these other letters. And so, what about that? Well, I'm staring at these other formulas and I say, okay, well, now I know A and C. And so there's a formula right there that lets me find E, that eccentricity number. So I say 27.7 equals A, which we said was 32 times E. So, and what I want you to notice is what kind of a number you get. When I divide that by 32, I get E is 0.887. So E is approximately 0.87. You may remember this from yesterday, but what did we do to create the ellipse yesterday? What was the ratio of M to N? We said it was less than 1. When it was equal to 1, that made an ellipse. And so the E value, which is, and I didn't say this explicitly yesterday, the ratio of the length from and I'll show you a Desmos for this in just a second. Actually, maybe I better show you right now. So here's another one that I made just this morning very quickly. So this E value, So notice the green, yesterday we had the green line, which was the distance from the center or the focus up to the point that's on the curve, and then the horizontal blue line to there. And notice they're different lengths right now. And yesterday, when those lengths were exactly the same, when E was 1, that actually produced a parabola. And so that's the one I drew for you in AutoCAD. This is the mathematical version of the same thing. But then I changed E to 0.75. Remember that? 0.75. And that actually created an ellipse. And so that happens when that green length is smaller. I said 0.75, but the 7 didn't show up. So that's exactly what we drew yesterday, except this is the mathematical version of it. So the green line is 75% of however long the blue line is. And so that's what eccentricity is. That's the sort of the technical definition. So if I make it 1, the ratio of those two lengths is 1, I get a parabola. If it's less than 1, I get this. Now, what I want you to notice is what happens if that number gets smaller. Now, of course, the fun part about this is I can just drag this thing, right? So I just want you to watch it as I make it smaller, 0.8, 0.7, 0.6, 0.5. Notice what happens when I get down there. What is it starting to look like? Notice if E is any place between, this is in our note sheet, but if E is any place between 0 and 1, it makes an ellipse. But if it's really close to 0, it actually makes a circle. In other words, the blue line is way longer than the green line. It makes a circle. It isn't quite a circle yet. It's still an ellipse, but it's close. I actually don't think, I think it's going to just not exist if I actually draw it at 0, just because, like, where's the graph? But what happens if it's more than 1? Notice if it's more than 1, well, you might think we just got a parabola again, but we didn't get a parabola because look, there's another side to it. So again, that's what E or eccentricity tells you. Maybe we'll play with that a little more in a second. So the fact that I got 0.87 here, if I understood what eccentricity means, I would say, well, of course it's less than 1. That's what ellipses are. So I'm not surprised that that happened. And let's see, what else can I figure out up there? Well, it looks like the only letter I don't know, I have A, B, C, E. There's 5 of them. The only one that I don't know is this D value right here. So D is equal to A over E, whatever that is. D equals A, which is 32 over E, which is 0.87. So 32 divided by 0.87 is 36.8. Is this note clear about what D is? What the heck is D? It is, just take a look at it. Notice right here, we're told the directrix, and notice it's plural, directrices, there's actually 2 of them. They say, oh yeah, the equation, the vertical directrix, if you wanted to know where that was, is at x equals D. So if I graphed the line x equals whatever we just got, 36.8, I would kind of put it over here. Remember, this distance was 32, so that's 32, 0. So if I went out to 36.8, somewhere in here, it's like that's where the directrix would be. Does that make sense? And then we were told the focus here, so we knew where that was. And so, you know, again, that's just like working our way backwards toward, you know, this line and that line, and that's making sure that the first one is 87% as big as the second one based on this E value. So it kind of allows you to sort of reverse engineer this, if you will, or, you know, given any limitation. Like in my case, my limitation started with, I sort of knew what A and B were. Does that make sense? I knew the size of the ellipse I wanted, and then it was like, okay, well, now I need to build it. I didn't need a directrix to build it because I sort of used the string technique. But I did need the focus, and so I sort of needed some of that. That's kind of the neat side of all of this. And then notice in this note too, it also tells us right here that eccentricity, if E is between 0 and 1, then you get an ellipse. If E is bigger than 1, then you get a hyperbola. Doesn't say parabola here because that isn't listed, because in this case, these formulas only apply to hyperbolas and ellipses. And so there isn't anything about parabolas, but you could sort of add to your thinking that if E is equal to 1, then you get a parabola. That's just kind of nice to have sitting here. So in this way, I can kind of, work my way around and figure out kind of what things work. And you'll notice in your assignment, that's kind of what the flavor of these questions are, is they'll just say something like, okay, we got this, we know where the focus is and we know what E is. Can you create the equation for the ellipse? That kind of, that's the flavor of the kind of questions. So let's just try something kind of not practical like that, just so that you're maybe a little bit better with the book question. I said copy, so how do I say paste? Can't I just recopy you? Can't right click because I don't have a mouse. Guess I'll just have to bring another one in. I just want a fresh note sheet, otherwise it's going to look like a mess. So I don't know, let's make something up. Again, I don't really need everything, so let's crop that thing off. Nice and big so you can see it. So I don't know, what if I gave you this? What if I told you the focus is at 0, 4 and 0, -4. I could write 0, 4 and 0, -4, but instead I'll just write 0 ± 4. So there's two focuses. There they are. And let me give you a vertex. What if I told you the vertex? Again, that's code for kind of the outside edge, the top, bottom, or the right, left. So if I told you the vertex or vertices, since they're plural, was at 0, 6 and 0, -6. What if I told you that? That's actually all I need to tell you. And you could actually find the equation for the ellipse. Could you stare at this note sheet and kind of, sketch / draw / find the equation for that ellipse based on that info that I just gave you? I'll give you a second.
So is this ellipse equation just based on the standard form, the ax squared plus bx, and then plus?
No, the easier
Okay.
form. In other words, because this one
Okay.
is centered at the origin, because
Mhm.
this is centered at the origin, its equation is really x squared over a squared plus y squared over b squared equals 1, because it's centered at the origin.
Okay.
So in other words, all I need to know is a and b, and I've got the equation. And incidentally, that information is conveyed on the previous page of my note sheet. And of course, the cool thing about this is you got Desmos, so you can, test out your own theory. If it doesn't work, you're going to know. So you may notice something a little confusing about this. Because we were told that in a sense, that's our situation. Hey, our focus is not at something zero, it's at zero something. In other words, this is vertical, so you're going up and down to get the focus. So in a sense, oh, this is my focus is on the y-axis then, okay. So why not throw in some graph paper? Make this thing accurate. So if I go up 4 and down 4, so there's my focuses, foci. So I see that this thing is going to have a vertical orientation. And then I'm told the vertices, in other words, the axis itself is at 0, 6. And so this is out here and this is out here. Now I can make a rough sketch of it, but do you understand? I don't know how wide to make it. In other words, is it a really high eccentricity? In other words, that would be an E value of like 0.9. That's really close to 1. So it's really flat. Halley's Comet has an eccentricity of, I think I looked this up or saw this on, I think I might have saw it on 3 Blue, 1 Brown, or whatever that one is. It's really good. But he actually listed what the eccentricity of Halley's Comet was. I just forgot it. It was like yesterday, but it was like 0.96 or something like that. Or it actually could be kind of a long, sort of a tall, a little bit more wider one, in which case maybe the eccentricity is like 0.3. See, the problem is I don't know what that is. That's so, but you can actually calculate all that stuff. Now, the thing that's to me confusing about this note, do you see that this disagrees with what I wrote here? That's not what I wanted to do. Like my gut reaction to this is to always kind of put the A under the X every single time, but notice they're saying, no, that's not the case. The A value is always the major axis value. To see they're kind of doing that a little bit differently. So if I was making this note sheet, I don't know what I'd done it this way. That's what I mean. Like you're sort of you're reading someone else's, you're singing someone else's song, you're reading someone else's poem, not your own poem. And so it's a little harder to keep this straight. So in this case, I guess they're saying, oh, okay, well, the A value, that's got to go with the Y. In other words, in a sense, I'm saying, oh, okay, I guess they want me to switch this. That's kind of the idea here, which is a little bit annoying. I find that kind of stuff hard to keep straight. So cool. Well, that means I already know what A is. It's 6. So that means I know the equation so far is x squared over something plus y squared over 6 squared. I think I'll write 6 squared. In other words, I know most of the equation right now. I just need to know what that other value is. And that's what I said a minute ago. In other words, am I aiming for 2 and 2? Is that how wide the ellipse is going to be? Is that its vertice, 2 and 2? Or is it actually 3 and 3? I mean, I got to figure that out. Well, again, that's where these formulas come in. This is not hard because don't we have that formula that allows us to convert? As long as I know either all the vertices as we did a minute ago, then I can find C. Well, in this case, I know C in one of the vertices, well, and I'll be able to find the other one. So, okay, cool. They're saying that B squared is equal to A squared, which is 36, minus C squared. 4 squared is 16. So, okay, it's the square root of 20. So B is the square root of 20, or B squared is 20. So that means I could just put a 20 down here. And maybe I'll, since I did that, rewrite that as 36. And so of course I find myself thinking, is that right? Is that correct? Also, you know, what is the square root of 20? If I wanted to make a graph of this, the square root of 20, you should be able to estimate that in your head, but it's approximately 4.5. So B is approximately 4.5. Well, now I know where to put this other point. 1, 2, 3, 4, 4.5. It's actually right there. 1, 2, 3, 4.5. It's right there. So my rough sketch, ellipses are really hard to sketch, but you always want to leave. Does it make sense? The slopes of those are horizontal and vertical. So you don't want to come to a point. When people are trying to sketch these, they always look terrible because they kind of go like that and come to a point. Like try to start and then just sketch between. It's a good skill to be able to at least reasonably sketch something. Notice you don't have to just draw it all in one pass. Like that's decent. If you draw super light with a pencil, then you could eventually go over it darkly once you kind of had something you like. Notice it's not great. It's kind of egg shaped, a little skinnier on the top than it is on the bottom. Could you guess the eccentricity for this based on what I said a minute ago? Are we talking about something that's more like E is 0.3 or E is 0.8? Remember, E equals 0.9 is super long and skinny. E equals 0.1 is more circle-ish. It's kind of approaching a circle. This looks closer to a circle to me, so I'm guessing. I can't really know this for sure, but I'm thinking it's more like 0.3 or something like that. And again, can't we figure this out? I'm not going to do it right now, but don't we have all the ingredients we need thanks to this little formula to actually know exactly what he is now? And in a sense, we should, when we get that, say, yeah, okay, I'm not really surprised. So eccentricity is a thing in the real world, because if you're an astronomer, that tells you something about the orbit of it. Notice in this case, we actually knew everything from the start. Since it happens that E is related to C and A, I could actually just take 4 and divide by 6. It's 4 6, it's 2/3. That's actually a lot bigger than I thought it was going to be. Isn't that, do you agree with that? I didn't think it was going to be that big. I thought it was going to be like 0.3. But if C is 4, and the A value here is actually 6, and it's 0.67. That's not what I thought. I don't have a good feel for E yet. I was thinking it was going to be way smaller than that. And of course, as I said, it'd be good to go graph that equation and make sure it really does what you thought it was going to do.
Yeah, mine came out good.
Sweet, worked.
Yep.
So the only thing your assignment's going to mix into this is, what if all this was true, but then they said something like, oh, by the way, it's centered. What if they sort of threw this, and this is the way you want to solve these problems? What if they kind of threw in that it was centered at the point 2, -7? Don't consider that at the start. Get it done. Like we got it. We got the ellipse now. Awesome. Well, now just go put it over there at 2, 2, 7. So if its center is no longer here, but I'm going to slide it right to, you should already know this. What do I need to do to the equation?
You subtract.
Because it's going right to, you might think it'd be +2, but it's actually -2. That'll slide it right to. And then it's going to go down 7. So instead of saying -7, you say +7. So, okay, great. There. It's the same exact ellipse. I just put it where you wanted it. Save that for later. So the note sheet, if you will, doesn't address that, but your homework assignment kind of asks you, gives you just a little bit of random information about your ellipse or hyperbola or something like that. And then says, all right, go to it. Hyperbolas are a little weirder. They're not near as practical. Incidentally, I didn't say this earlier, but it's kind of a cool point. This elliptical shape right here is the way a lot of arches were built. And I got to go to Ireland about 5 years ago. It was really cool to see, a country that has actually really old architecture. And so their bridges and archways they were not there just for looks. Like in my house, the whole house already stood. I just put it in there to make it look nice. But back in the day, when you wanted a hole in something, it's pretty hard to get it to support. And so they actually came back and put a keystone at the top of this, and then just started kind of stacking stones against this. They would actually build a framework underneath it to stack the stones on. And all the stones would kind of go around here like this. And in the case of, like a roadway, like a bridge, they would stack more of them on top of that. And maybe what's going underneath that is a river or something like that. And then you could actually take that structure out. And because the rocks are all pushing together, does it make sense? It doesn't fall and cave in. Well, the brilliance of that shape is it actually took the weight, because it turned vertically right here at the end. It took the weight and put the weight straight down. You future engineers, if you do a circular arch that actually takes off at an angle like this, does it make sense when you put weight up here, the weight of the roof or the weight of the road, if this is a bridge over a river or something like that, does it make sense it's actually going to take that weight and sort of push the wall out? Like the wall's going to want to fall over now because there's weight pushing it out sideways, and so it wants to tip over. Whereas the brilliance of this shape is that it's actually vertical at the end, so it puts the weight straight down, so it doesn't have a tendency to want to tip the walls out. So anytime they built a building that was huge, like a church or something like that, where they want a whole bunch of space inside it, the arches were always at least elliptical. There's a couple other curves that are cool too. Catenary curves are amazing. But that was kind of the brilliance of that design. So this is a very ubiquitous shape in architecture when you build out of rocks and stuff. So I find ellipses much more interesting than hyperbolas. But let's do one kind of hyperbola related question. What if I said, let's find a hyperbola. Let's spell hyperbola with a Y in it like it's supposed to be. And I gave you the fact that, let's kind of do something similar to a second ago and see if we can survive this. Like if I told you the focus of this is at ±5, 0. So there's two focuses for this. And the vertex, I'll say vertexes, even though that's wrong. The vertexes are at ±3, 0. So if that's going to end up as a hyperbola, and then maybe afterwards we'll slide it to some other location or something like that. Again, the question really comes down to, is it a hyperbola that's kind of long and skinny like this, or is it, really long and wide like that? Are they close together, far apart? Again, that's what the directrix and the focuses and stuff are telling us. And is it left, right, or is it up, down? Is it like this? Is it actually up, down as a hyperbola, or is it left, right? So this only works centered at the origin. So if you graph the points, that should at least get you started. And if you understand from the playing we did in AutoCAD, and again, I'm still going to give you a little bit more time to think here. Given that those red points are the focuses and the vertex is at 3, well, again, the vertex is where something turns around, and as you know from earlier. And so basically what we're being told is, oh, okay, I see it now. It looks something like this. It's kind of a left right, so to speak. So it's something like that. I don't know how steep it is. Is it skinny? Is it, is it really more steeper like this? I don't know that yet, but at least I have a rough idea of what this thing looks like. What should bother you is, dang, because of the minus sign, it's kind of like this effectively should be your next thought, is like, I know it looks like this. It's exactly the same as the ellipse, except there's a minus sign. And the problem with the minus sign is which one gets it? Is it that one? Because if it was one way it was like left, right, and the other way it was like up, down, right? So, I mean, again, in the world we live in, I would say just get out Desmos and go make one, and make your note sheet for yourself. Like, don't cheat. But if I'm taking a test or whatever, something like that, I mean, this is what my note sheet is designed to do. So ours has a horizontal major axis, and I think the major axis is much less obvious in a hyperbola than an ellipse. Ellipse is like the long one. Yeah, that's the one that's major. But ours has a horizontal major axis. And so, oh, okay, it's the y value that got the minus sign, then not the x value. So what I just wrote down, I had a 50-50 chance. I got it right. And I didn't have that memorized. I didn't know. I'm not sure what the answer was. And so, okay, cool. So I have it basically correct. Like this is what it is. I just need to know what values for A and B. Well, what do I know? Again, I'm looking at these formulas down at the bottom. What do I know? I was told that the focus was plus or minus 5, 0. And the focus was on the x-axis. And so I'm kind of looking at this note saying, oh, okay, C is 5. So there's a clue that I need to include. C is 5. And then I was told the vertice, the major axis vertice, I was told that was plus or minus a 0. So that for me was 3. And so I know A is 3 now. Whoops. And so now these formulas take over. Given any 2 of these 5 parameters, I can now find anything I want. So now I can take off and just either reason for myself a little bit or maybe rely on these formulas a little bit. So for a hyperbola, this is my connection between A, B, and C. So since I have A and C, this is going to allow me to get B. That's kind of cool. So awesome. That means B squared is equal to C squared, which is 25, minus A squared, which is 9. This time we got lucky because we came out with a perfect whole number. So B is actually 4. So now I think I have the equation for this. Again, based on the way this book does this, I'm a little, I don't know, nervous about which one is which. In other words, do I have it right? Is A 3? Or is it backwards? Is this one the 3 and this one's the 4? There, I got my equation. And so I could go on to find out, where's the location of the directrix. I could put that on here if I wanted to. Fine. I could find the eccentricity of this if I wanted to. Fine. But again, after this, if you wanted to slide it away from 0, 0 and go put it somewhere else, fine. Switch out x squared for x plus 7 squared or whatever. So I find this really, on a personal level, just really dull when it gets turned into book problems like this and so forth. I mean, I want you to be able to do them. That's worth something. But I'd far rather go, build elliptical arches and build machinery that's based off of this. And so, of course, now that I have the equation, then I could actually get an accurate graph for this, right? My blue graph was just a rough sketch, but it's probably too steep or not steep enough or whatever. Interesting. Okay. Now, you don't have any equation, you don't have any questions about this in your assignment, but I just want to do something kind of fun going out the door. And this is in the note sheet, and I'm referring to this. And this is one of the problems, like I would be assigning questions about this, except for there aren't any in my open math. It's not as big as a problem. You don't have as many problems to choose from, but the polar form of these, like you can write all of these. Remember, we said, hey, everything we just did is in rectangular, and you can write these in polar form. Notice you have this just page of really complex looking, ugly problems. And so let's just kind of play around with that for a few minutes. Well, just for the fun of it. I say just for the fun of it, I'm not giving you a homework assignment, but I could give you a test question on it. As long as I keep it simple, because I'm not really giving you a chance to practice that much with it. But let's just kind of play with that for a second. And let me show you kind of the brilliance of this idea, because you should sort of stare at that and say, where in the world did all that come from? And we did say that, well, we have this, you know, X and Y equation up here. And so we know how to replace X and Y with R's and thetas. Remember, X is equal to R cosine of theta and Y was equal to R sine of theta. So I could replace that and then it would be in R's. And so let's just kind of do that for a second here and just sort of mess around. Have some fun. Like, so I'm saying that first equation that we just got is x squared over 9 minus y squared over 16 equals 1. And we said that's a hyperbola. And so we say, okay, well, let's make it polar. And you may remember, as I said, that x is equal to r cosine of theta and y is equal to r sine of theta. And so that's my way of getting rid of x's and y's. And so, okay, great. So I go down here and I say, so then in polar form, I guess that would be r squared cosine squared theta over 9 minus r squared sine squared theta over 16, and that all equals 1. So I'm in polar now. Mission accomplished. I can't graph this in Desmos. I can't graph this on my graphing calculator and cheat because it's not solved for R. So I'd have to solve this for R somehow. That's not terribly hard. So let's just play with that for a second. Since they both have an R, I can factor it out, right? So I have an R squared factored out. And then that leaves all the other junk behind. Cosine squared theta over 9 minus sine squared theta over 16 equals 1. And then I guess I could divide. Since I'm trying to solve for R, I could divide by all of that. And I could mess around with this some more. And I could look for identities. Like I remember there was one for cosine squared minus sine squared. I could multiply the top and the bottom of this equation by something that gets rid of the fact that there's fractions over fractions. I could certainly take the square root of both sides. And, you know, now I have it solved for R, but when I take the square root, I might lose part of it. Does that make sense to you? Because if I have something like, you know, x squared equals 9, then that, which is totally unrelated, the answers to that are 3 and -3. But if I square root both sides, I only get 3. Like I lose half my answers. And so if I try to graph this, I might not get the entire graph. I wish Desmos was sophisticated enough to let you type in R squared, not just R. I don't think it does. Maybe I'm wrong. Let's see, cosine 9. Let's go try to just see what happens if I graph this. So first of all, does it let me do R squared? I have in my head the answer to this is no, but let's find out. Equals 1 divided by cosine squared. Anybody know the answer to this? Can I get away with putting the, I guess I can't.
Yeah, when I tried it, I couldn't get it to work. You just
With
square
R
root the
squared?
other side.
Yeah, so notice it's got a caution, like polar equations must be linear in R, meaning solve for R. And so therefore, okay, fine. That means I'm gonna have to square root both sides, which I can do. So unfortunately, I have to start with a square root. Do you think this is gonna work? That's my question. So cosine, anybody know, can I get away with this? Can I type cosine of theta Like, that's not where I want the squared. Is that okay? Anybody know? Does that think, because remember, this is not theta squared and then take the cosine of it. That's not what I mean. So I guess I could test it by putting an extra set of parentheses in here, right? And see if I get a different graph. And I didn't, so that means I can be lazy and not have that, right? But that's kind of poor form. And so then that whole mess was divided by 9, if I remember right. Then I had to go back and subtract from that sine squared. Divided by 16. And so there we go. And so notice, hey, that actually worked, didn't it? So it doesn't seem like the fact that I took the square root of both sides screwed the graph up somehow. So that's okay. Sometimes it's okay and sometimes it's not. But notice it actually goes through the points 3, 0, and 0, 3. So it worked. All right. Awesome. But notice how weird that looks in comparison to what the note sheet that I referred to. Notice how weird that looks compared to this. Notice there's no square roots, there's no sine squared, there's no cosine squared. And not only that, it's got the E in it. Like, that's kind of cool. If it's got E in it, then I could actually just read the eccentricity right out of it. So it's like, and they're saying this is what, they're basically saying this is what these conic sections look like. And notice it's the same exact equation for all of them. Like, that's parabolas, ellipses, it's everything. What? That makes no sense. I mean, how do I get to there? Like, my equation looks so much more complicated. Does that make sense? Like, what the heck is going on here? So I just want to play with that for a second because it's kind of brilliant. So we tried it and it works, surprisingly. But let me show you another way. And I didn't invent this. This kind of bothers me a little bit because it feels like I should be able to do something to this to get it to look like that, like get rid of the squares and square roots and so forth. And as I said, we have sine squared and cosine squared, and there's an identities about that. So maybe I could start messing with those and like switch out cosine squared for 1 minus sine squared, or switch cosine squared minus sine squared, and like play with it, like try to write it in a simpler form. And so it feels like maybe that would be possible. But what I want to show you is how to kind of cut to the chase a little bit. Since all of these were based, so let's go try to find just one equation for all of them. So just to keep it simple, I've been drawing this thing to the left every single time just to kind of help with your thinking. And over here is our directrix. And this is sideways, and so our axis is cruising along here. So let's play with this for a second. So we got our focus. And so the points on this graph were effectively determined by this distance and blue. It's already blue. What am I doing? Green, red, brown. Let's go brown. And that distance, right? So in this drawing right here, because I drew the blue significantly shorter than the brown, what would this produce if I kept with that ratio? Is this an ellipse, a parabola, or a hyperbola? E is blue length divided by brown length based on the drawing. What kind of a number am I going to get if I divide the blue length by the brown length?
I think it's going to be an ellipse. The number will be less than 1.
It's going to be less than 1 because blue is shorter than brown. So when I divide those, I'm going to get something less than 1, and that will produce an ellipse. So this is an ellipse that this is the creation of an ellipse that I just drew. And notice, as I said, you can't tell yet, like that. You can't tell it. Could this be visually? Is that an ellipse, a parabola, or a hyperbola? I can't tell. They all are just interesting curves, kind of similar to the same thing. Well, do you agree in polar? This is really cool. In polar, isn't the distance from the XY axis, and I guess I'll go in and draw the XY axis in here now. Isn't the distance from the center of the XY axis, from the origin to the curve, isn't that what we called R? So that's why I threw R in there. And then secondly, isn't this angle right here the angle? So for polar, isn't that what the issue is? The length R, how far is it? We're defining that blue point that's on the curve as how far is it away and what angle is it to create my points. So, and then as far as some of the note sheet things we just looked at, this distance right here is distance D. That's the distance from the origin to the directrix. Like these are kind of the ingredients we have to work with. So here's something really powerful then. So I got to come up with some relationship that kind of merits all of this. And so I need I think rather than kind of, I don't know what letter to use up here. I'm just going to use question mark. I need some reference, something for that, because don't I know that R divided by that is what we're calling E? Isn't that what E is? Is eccentricity is those two things divided. And so this is my ingredients. This is basically all the things that I have to work with. And so now I want to try to come up with an equation. It's kind of a polar equation for this generic curve that we ultimately don't know what it is yet. Now, based on this picture, this is kind of powerful. I hope you can see this because it's kind of neat. If I drop this down 90 degrees, that creates a right triangle. And would you agree that this length right here would be R times the cosine of theta? I mean, isn't that the X coordinate? So I can know that. That's kind of fun. And if I know that, would you agree that this length here plus this length up here is equal to this length down here? So let's write that out. So that means question mark plus R times the cosine of theta would have to be equal to D. So that means that length up there, that question mark, could actually be kind of rewritten. Instead of making up a brand new letter that I don't want, I could rewrite it as D minus R cosine of theta. Okay, cool. Well, if that's true, then let's take that. Let's take this guy right here and throw it in up there. And now I have a formula that has everything that I need. And so what do I have? Well, I have R divided by the question mark length, which we now have an algebraic formula for, and that's equal to E. That's an equation that has R's and thetas in it. Notice it just has R, not R squared. That's kind of nice. And it's got D and E, but those are just constants. D tells me where the directrix is, and E tells me what the eccentricity is. That's rather cool. So someone's knocking at my door. You take a second then and solve that for R. Notice there's two R's. So solving for R is not super simple, but you're good at algebra. You should find that easy. Be right back. No. Yeah. Did you succeed? And notice, and don't forget, we have not chosen what this is yet, right? We haven't said this is an ellipse, this is a parabola, whatever. So let's do this because it's fun. So if I take, I don't like fractions. So if I multiply both sides by d minus r cosine of theta, if I multiply e times d, I get e times d. If I multiply e times r cosine of theta, I get that. So there I multiply both sides by d minus r cosine of theta. Now I want to solve for r, so I get all the r's on the same side by adding them to the other side, and this is starting to look like that sheet. Now I can factor r out, leaving 1 plus e cosine of theta. And now I can solve for r by dividing, and so I get e times d over 1 plus e cosine of theta. Boom, this is all conics. All conics. That's cool. Wait a second. All conics. How come there's 4 equations? I just said it was all of them. How come there's 4 of them? Well, they're almost all the same, or at least they're close to the same. But why is there 4 of them? Well, notice there's an assumption in what I just drew, in the sense that, you know, where's our parabola? If this is a parabola, well, it's facing left. Well, aren't there parabolas that face right and up and down? That's why there's 4. Aren't there ellipses that are horizontal and kind of take off to the left, as this one does of the directrix? But then there's ones that take off to the right, and then there's ones that take off up and ones that take off down. And so that's why there's actually kind of 4 of them, so to speak. But isn't that cool? Like, isn't that amazing that that's literally one equation in polar form that works for all of them? And there's a part of me that thinks this is superior. I don't know which one is superior, but I never like squareds because those like cause a lot of problems. And so that's kind of interesting. Well, let's play with this a second and use it for something, and then we'll get out of here. But so I made one other playful, was it this one? This one. So let's watch this in action. So notice E, and I couldn't use lowercase e because lowercase e is, well, 2.718. So I still wanted to use E, but I just thought I'll use capital E. So notice the directrix of this says D equals 4, the directrix as it 4. And T is theta. I couldn't use theta because it doesn't like that as a variable. It doesn't let me use that. So notice I can kind of slide my point any place I want to. And so what's happening here? Remember that what's happening is the ratio between the length of the green line divided by the length of the blue line is staying 1.5. Can you see that happening visually? Does it look like green is 50% bigger? Well, actually, I just screwed up the proportions. Let me go back and hit zoom square. Does it look like the green is 50% larger than the blue? If I go to some other location, does it still look that way? The answer is, yep, it does. Like that's what's creating this shape. Now, because that E value is more than 1, what is this shape? Is it am I just seeing the edge, the end of a ellipse or a parabola or a hyperbola? You should know the answer to that based on what we've been playing around with. The answer is if it is less than 1, it's an ellipse. If it's equal to 1, it's a parabola. If it's more than 1, it's a hyperbola. So this is a hyperbola. If I back out, oh, yep, look, there's the rest of it. Okay, that's cool. And so what's going to happen, and this is kind of fun with Desmos, is, what does it change if I kind of move the directrix to a new location? Notice the focus doesn't move. The focus to have a simple equation like this, the focus has to stay at 0, has to stay at the origin. But you'll notice it gets kind of taller, whereas it gets pointier, if you will, the closer I get to it. So that's kind of interesting. And then if I make the eccentricity way bigger than 1, notice it kind of makes it look steeper and steeper and steeper. Again, right there, when it popped to 1, I just lost the other side of my shape. That's because it just turned into a parabola. If I keep going lower than 1, boom, the parabola like closes off. So it's, if I make this like 0.95 or something like that, notice that's really close to 1. So this is kind of what's called a high eccentricity. This is a high eccentricity orbit. This would look like Halley's Comet, as I said, with the sun at the focus over there, and then most of the time it's out in the space and doesn't come back. And so this is a pretty powerful idea. Notice though that this equation that I stuck in up here, that I kind of hid in this folder, is the one we just built. E times d over 1 plus e cosine of theta. I just built the one that kind of worked its way to the left. But let's see. But there are others. And so let's just play with this for real quick. Let's just do kind of one problem. So I'm going to take a quick snapshot of this. So if I just kind of lean on the note sheet, if you will, and not kind of thorough understanding, what if I ask you for this? If I say, here's an equation, r equals 9 over 2 plus 4 sine of theta. You should vaguely say, hey, that's one of those shapes we've been studying. Awesome. But I don't know which one exactly. So let me throw this note sheet in here for us. Crop that baby down to the part we're interested in right now. Make it a little larger so you can see it. Can you rework that a little bit so that you actually kind of know what that is? Notice how you can't tell what E is just yet. Like you got to work at it a little bit, but knowing what E is the most important part. If it's less than 1, you know what it is. If it's more than 1, you know what it is. So notice it's got sine and not cosine. So what does that say? The conic section with a focus at the origin and eccentricity E has a polar equation. Well, it's like that didn't tell me anything. What does this mean down here though? If one directrix is y of d, down here the directrixes are y equations. Up here the directrixes are x equations. A second ago we had the equation x equals and it was vertical, a vertical directrix, and so that caused it to kind of work its way left and right. Oh, this one is y equals, it's a horizontal directrix, so this one's going to be like an up and down one. Does that make sense? It's kind of up and downish because it's a sine, so that's how we get sine. And then notice they're exactly the same equation except for this little sign right here. It's either a plus or a minus. Oh, I got a plus sign. So I'm over here, right? Mine looks like that. Now, you also notice there's a 1 there. Like we don't have a 1, we've got a 2. That's not good. We need a 1. How are we going to get a 1? Mark it out. Easy. What do you do?
Factor out a 2.
Yeah, or even easier, divide the top and the bottom by 2. so that I can get rid of it. It's a fraction, right? So I'm going to divide the top by 2, which is not so great because it created a fraction. And then because of distributive law, I've got to divide the 2 by 2. There's my 1. And I got lucky here, divide the 4 by 2 and I get 2. So now it's kind of in the right form. What can we learn from that form? Well, notice the number in front of the sign is E. So that's kind of cool. I know E is 2. Well, now you know something, right? If E is greater than 1, it's a hyperbola. So this is a hyperbola. That's kind of fun. And you could know where the directrix was if you wanted to, if that was part of the question. Because the top is E times D. So since E times D, since E times D is equal to 9/2 for us, and we know E is 2, then D would be equal to 9/4. So I could graph the line y equals 9/4. And hyperbola. Kind of get on with it. Cool. Okay, so today would be Wednesday. Tomorrow would be review for test day. The test, as the syllabus shows, will be Monday. There isn't a good reason why I can't just have your test be anytime Monday. So I think I'm going to just let you take it when you want to Monday. I had a few, I sent you all an email because I talked to the board last night, the board of our school, about, you know, what's working and what's not working for students and teachers in this kind of new environment. And a few of you responded to that. And a few of you said, you know, one of the things that's not working, especially with the morning class like this, is it's kind of a bummer to have to take that test super early because you're not thinking as clearly, those kinds of things. But I don't see any reason we can't just go back to that. So basically the test will be any 2-hour time slot. I think it was 2 hours, 2.5 hours. Any 2-hour time slot on Monday you want to take it, it's fine. So anyway, we'll review for that tomorrow. The review's already up, and certainly ask me any homework questions. We can talk about homework if there's curve balls in the 12.4 conics section assignment. We could talk about those. But I think that'll do it. So get on out of here.
Thanks, Doug.
Thank you all. Have a good day.
You too.
Thank you, Doug.
You are welcome. Thank you.
See you tomorrow.
See you tomorrow.